Our last lesson of chapter 8, 8.6. So what we're going to do is use what we have learned about counting and about combinations and apply it to probability. So the first thing that I want to do is talk about a little bit of terminology. So you're familiar with the terms that you'll see when you're asked to do problems that have to do with probability. And then we're going to talk about different ways of calculating different kinds of probabilities. So the first couple of things are just terms. So for when we're talking about probability, anything where we don't know the outcome, we call an experiment. So something where we don't know the outcome. So we talk about doing an experiment. So when we're talking about probability, flipping a coin would be an experiment because we don't know the outcome. The possible results of the experiment the results are called outcomes. So we do an experiment, whatever happens, whatever comes out of the experiment is our outcome. The set of all possible outcomes, so everything that's possible, is called the sample space. So if we were flipping a coin and rolling a die, the sample space would be every combination of heads and tails and the number 1 through 6. That would be our sample space. All of those possibilities would be our sample space for that particular experiment. A piece of the sample space, one part of the sample space is called an event. So an event in the sample space that we just talked about would be one possibility of a combination between the heads and the tails and the 1 through 6. So that would be an event in that sample space. So just so we're familiar with the terms that you'll see that have to do with probability. So let's define what we mean by probability. The way we're going to calculate. So let's say we have an event with a certain number of equally likely outcomes. So our probability is the number of favorable outcomes so those are the ones that we're interested in, divided by the number of possible outcomes, the total possible outcomes. So, for example, if we're flipping a coin, the number of total possible outcomes is just 2. It can either be heads or tails. We're rolling one die. the total number of possible outcomes would be 6, because we have the numbers 1 through 6. So our probability is the number of favorable outcomes, those are the ones we're interested in, and we're dividing by the total number of possible outcomes. And this is where what we talked about with counting comes into play, because depending on how we're finding our probabilities, we need to figure out how to count up the number of favorable outcomes, how to count up the number of possible outcomes. So that's where all the stuff we talked about with counting comes into play. Our probability is always going to be a number between 0 and 1. And if we write it as a percent, it would be between 0 and 100%. Probability of 0. If we get a probability of 0, what does that tell us? Not possible. It's impossible. It cannot happen. And a probability of 1, what does that tell us? It means it's, what was it? Certain to happen. It has to happen. Means certain. It has to happen. So if you calculate probability and you get something that's not between 0 and 1, you know you've made a mistake. Because it would be nice to have to know about something that gives you a probability of 2. So what we're going to do is just do a few examples. We'll start with some easy examples of calculating probabilities, and then we'll just, as we go on, we'll talk about more complicated scenarios, and we'll talk about how we combine probabilities of different kinds of events together. So questions on what we've talked about so far. It's our basic idea of probability. Probability is one of those subjects that you have to think a little differently. It's a different way of thinking than a lot of what we've done, and it can be kind of challenging. But what we'll do with it is pretty easy kind of probability, but you can get very complicated very quickly with probability. All right, so let's look at a few easy examples. So let's say we draw a card from a regular deck of playing cards. Draw one card from a deck. We want the probability, and usually we write probability of whatever the event is in parentheses. Probability of drawing a king. So we need to know for a deck of cards, let's start with the easy one, how many total possible outcomes are there for drawing one card? 52. There are 52 cards in the deck. And the favorable outcomes, how many kings do we have? 4. So our probability of drawing a king is 4 out of 52, or 1 out of 13. We have a 1 in 13 chance of drawing a king if we draw one card. How about the probability of drawing a club if we draw one card? So we know that there are still, our total number of possible outcomes is 52 cards. How many clubs are there? 13. We're divided, the deck is divided into 4 suits. So there are 13 of them. And when we reduce that, 13 out of 52 is 1 in 4. 1/4 of the cards are clubs. So those are a couple pretty easy probabilities. All right, let's roll some die now. So we roll 2 6-sided die. And I like, our book calls them die. In the other book, in the geometry book, they call them standard number cubes. So we roll 2 6-sided die. We want the probability of a total of 4. So we add the two numbers up that add the two numbers that come up, and we want the probability of 4. So we want the probability of 4. So what we can do with die, with an easy example like this, is we can just list out the possibilities. So first off, let's figure out our total number of outcomes. So how many ways can 2 die come up? First one could come up how many ways? 6. Second one can come up 6. So we multiply, right? So our total number of ways that these two can come up are 36. We have 36 possibilities. And then we're going to just list out the possibilities for getting a 4. So what are some combinations that give us a 4? 1 and 3, 2 and 2, and then a 3 and 1. So those are our possibilities. So we get 3 possibilities that give us a total of 4. So our probability is 3 out of 36, or 1 in 12. Probability of rolling 4 is 1 in 12. Well, now we want to count how many ways. The next probability we want is what's the probability of rolling less than 4? We know there are 36 total ways, so let's count how many ways we can get a total less than 4. 1 and 1, 1 and 2, and a 2 and 1. So those are the ways we could roll less than 4. So we get a 3 out of 36 possibilities again, or 1 in 12. So our probability of rolling less than 4 is 1 in 12. Probability of rolling 4 is 1 in 12 also. Questions so far? All right, let's calculate a couple little more complicated probabilities where the counting gets a little more difficult. So for this example, we have a group of 4 boys and 5 girls. And we want to pick a committee of 3. All right, so we have a larger group, 4 boys and 5 girls, and we're picking a smaller group from that larger group. So what should we be thinking right away? How did we count things when we were picking the smaller group out of a larger group? Do we remember? When we picked how many ways could we make a committee of 3 out of a class of 30? How do we count that? Well, it had to do with factorials. And the fact that we're talking about a committee and not a president, a vice president, and a secretary gives us a hint that we're talking about combinations. We're picking a smaller group out of a larger group. The order doesn't matter, so we're talking about combinations here. We want the probability that the committee is all boys. So I'm going to say probability of boys equals, well, let's calculate our total number of possibilities. How are we going to find our total number of possibilities here? 9 choose 3. It's all the possible ways that we could have 3 people out of these 9. We have 9 people, and we're making a committee of 3. So the total number of possibilities is 9C3. And our favorable possibilities the number of favorable possibilities. How are we going to find that? Well, it has to be 3 boys. How many total boys do we have? 4. So it's going to be 4. Choose 3. The number of different ways that we could arrange 3 of those boys out of the total of 4. Those would be our favorable possibilities. All the different arrangements of 3 of those boys out of 4. So our probability here would be 4 choose 3 over 9 choose 4. And if we simplify this, let's do this one. Let's do this one by hand. So 4 choose 3 is 4 factorial over 3 factorial, and 4 minus 3 factorial is 1 factorial, divided by 9 factorial over 3 factorial, and 9 minus 3 is 6 factorial. We're gonna find our probability here by hand. Well, 4 factorial divided by 3 factorial is what? What am I left with when I divide 4 factorial by 3 factorial? 4. I just am left with 4. So for my numerator, I get 4. I'm going to write the 9 factorial as 6 factorial times 7 times 8 times 9. And that's divided by 6 factorial times 3 times 2 times 1. Well, those cancel. I can cancel the 2 with the 8 and I get a 4. And I can cancel the 3 with the 9 and I get a 3. So I get, my probability is 4 over 7 times 4 times 3, which is 84. So 4 out of 84 or 1 out of 21. So there's a 1 in 21 chance that all 3 of those boys on the, all 3 of the people on the committee would be boys. Questions on how we came up with that? Okay, let's look at a probability kind of like this that has to do with cards. So let's say we have a 5 card hand. And we want the probability of exactly 2 2s in that hand. So let's calculate our, let's count up our ways. So our probability is going to be, well, what is our total number? How do we find our total number of possible outcomes? We have a 5 card hand, and how many cards are we picking those 5 from? 52. So our denominator is going to be 52 choose 5. So all the different ways we could arrange those 52 cards into groups of 5. Well, we want 2 2s in our hand. How many 2s are in the deck? 4 2s. So we could arrange those 4 2s. We're picking them 2 at a time. So in the numerator, we're going to get a 4 choose 2. Because we can take those 4 cards and we could arrange them in groups of 2 in those different ways. But for each of those groups of 4 choose 2, we also have all the different ways that the other 3 cards could be arranged. So once we have those cards out of there, how many cards do we have left to choose from? if we're arranging these four cards in various different ways, how many other cards do we have to arrange for the rest of the hand? How many? Well, we're arranging, so we have 52 cards. We're arranging 4 of them in groups of 2. So once we've taken those 4 out, those 4 possibilities, so the other 3 cards can't be 2s because we're having exactly 2. So this takes care of the exactly 2. So how many are left if we exclude the 2s? 48. So we're going to multiply this by 48, choose 3. Because those other 48 cards, the 3 cards can be picked out of those 48 cards. They can be arranged in all of these different ways. So the total number of favorable outcomes are the number of ways that we could arrange the 2 cards times the different number of ways we could arrange the remaining cards in groups of 3. So the probability would be 4 choose 2 times 48 choose 3 over 52 choose 5. And I didn't calculate this out, but this would be our probability. So in that numerator, we have to account for the number of ways we could arrange the 2s and multiply that by the number of ways we could arrange the remaining 3 cards. Just like, and so this is we could think of this like we talked about with our shirts and our pants. We had 4 shirts and 3 pairs of pants. The total number of ways we could arrange our outfits would be 3 times 4. We can arrange the 2s in this number of ways. We can arrange the other 3 cards in this number of ways. We have to multiply to find the total number of arrangements. All right, so this is about as complicated a probability as we will have to think about in the homework. All right, questions there? All right, let's talk about a couple. So now we want to talk about how we combine different kinds of probabilities. So we've been talking about one event. We have a 5-card hand. We roll a pair of die. So we have one event. We want to talk about how we combine probabilities from multiple events. First kind is called mutually exclusive. Mutually exclusive events means that the events cannot happen together. So some easy examples of mutually exclusive events. If we roll one die, we can't roll a 6 and a 2 at the same time. If we pick one card out of a deck of cards, we can't draw out a 2 and a 3 at the same time if we're picking one card. So those would be mutually exclusive events. We can't flip a coin and get a heads and a tails in one flip. So those are mutually exclusive. So we're going to say, to combine our probabilities, we're going to say A and B are mutually exclusive. The probability of A or B happening, and we also write this as a probability of, you'll see it written as A union B. These two mean the same thing. Is the probability of A plus the probability of B. If we have mutually exclusive events that cannot happen at the same time, we combine their probabilities by adding. And what I always tell the students is we find OR probabilities by adding. That's going to be our keyword. It'll say, the problem will ask you OR. Probability of this happening or that happening. The probability of rolling a 2 or a 6. The probability of drawing out a 2 or a 3. That would be our clue. So mutually exclusive events cannot happen together. We combine their probabilities by adding. Well, sometimes we have events where the outcomes overlap. And I call those overlapping probabilities. So when we're talking about overlapping probabilities, that means two events share some outcomes. So an overlapping probability would be the probability of drawing a red card or a king. Some red cards are also kings. So they have overlapping outcomes. They share some outcomes. So to combine our probabilities here, if we have overlapping outcomes, so we're going to say A and B share outcomes. The probability of A or B, and it's the same thing that we write here. Probability of A union B is the probability of A plus the probability of B minus, we need to subtract the probability of the outcomes that they share, minus the probability of A and B. And the other way that you'll see this written is probability of A plus the probability of B minus the probability of A intersecting. These mean the same thing. So for the example we used, the red card or a king. So the probability of a red card or a king, if we add the two probabilities, the probability of a red card includes the red cards that are kings. The probability of the kings includes the kings that are red cards. So this probability counts those overlapping events twice. So we have to subtract the events, the probability of the events that overlap to get the probability of the two, because these count the overlapping probabilities. Questions there? All right, so let's look at a couple of examples using mutually exclusive events and one where we have to talk about an overlapping probability. So let's say we roll two die. And we want the probability of a total of more than 10. Well, we could list all of our combinations of two numbers that add up to more than 10 and count them up, but we want to save ourselves some work. So let's think about another way we could say a total of more than 10. What's the highest total we can get on two die? 12. So what's another way we could say the probability of rolling more than 10? Probability of rolling, what is it? 11 or 12. So this is the same as the probability of 11 or 12. Those are the only two possibilities that are more than 10. Is rolling an 11 and a 12, are they mutually exclusive? Could we roll an 11 and a 12 at the same time? No. So these are going to be mutually exclusive events. If If you figure out how to roll an 11 and a 12 at the same time, you'll probably go to Vegas and make lots of money. So these are mutually exclusive, so we combine their probabilities by adding. So we want the probability of an 11 plus the probability of rolling a 12. So with two die, how many ways could we get an 11? We could get a, what's that?
6 and 5.
A 6 and a 5, or a 5 and a 6. So we have 2 out of 36. How many ways can we get a 12? 1. Just a 6 and a 6. So our total probability is going to be 3 out of 36, or 1 out of 12. We have a 1 in 12 chance of rolling an 11 or 12. Questions on that example? All right, let's look at an overlapping probability. So we draw one card from a deck. We want the probability of a club or a face card. Well, some clubs are face cards, right? Some of the clubs are face cards. So this is going to be these have overlapping events, overlapping outcomes. So what we need to do is find the probability of a club plus the probability of a face card minus the probability of a club and a face card. So what's the probability of drawing a club? How many clubs do we have in the deck? 13 out of 52. How many face cards? King, Queen, Jack, 4 suits. So 12. So we have 12 out of 52. And how many clubs are face cards? 3. So we have a King, Queen, and Jack of clubs. So we combine those together. 13 plus 12 minus 3 is 22 out of 52. And we can reduce that to 11 out of 26. So we have an 11 in 26 chance of drawing a club or a face card. Questions there? All right, we have two other things to talk about: independent events and the complement of an event, and they're pretty easy ideas. All right, so let's talk about independent events. Independent events are ones whose outcomes don't affect the other. So a couple of independent events examples, easy examples of independent events: flipping a coin and rolling a die. What happens with the coin doesn't change what happens with the die. Drawing a card out of the deck and rolling a die. The two don't change each other. So those are independent events. And dependent events are related to the idea of replacement versus non-replacement. So drawing one card out of the deck, not replacing it, and then drawing another card out of the deck, those two would not be independent events because taking that first card out of the deck changes the total number of cards in the deck. So it's going to change the probability for the second event. So that would be an example of a dependent event. So dependent events are related to the idea of replacement versus non-replacement. Well, independent events, the probability of one doesn't change the other. So to combine the probabilities when we have independent events, we're going to say A and B are independent. The probability of A and B is the probability of A times the probability of B. And this is the kind of probability that we're probably most, no pun intended, probably most familiar with, is independent events. So the probability of flipping heads when we flip a coin is 1/2. The probability of flipping two heads in a row, 1/2 times 1/2, 1/4. So that's the most common, the one that we're most familiar with is the probability of combining independent events. So let's do an easy example that has to do with independent events, and then we'll talk about the complement of an event. So let's say we flip a coin. Let's say we flip a coin 4 times. We want the probability of all heads. So we flip it 4 times. We want the probability that every time we flip the coin, it comes up a head. Well, the probability is going to be what's the probability of getting a head on the first toss? 1/2. Second toss? 1/2. The flipping a coin the first time doesn't change the outcome on the second time. The third time, 1/2. Fourth time, 1/2. So we get 1/2 to the 4th, which is 1/16. So we get 1 in 16 chance that when we flip a coin 4 times, it comes up all heads. Questions there? Okay, last concept for today, the complement of an event. And notice we're spelling complement with an E, so it's not saying, hey, that was a really nice event. Looked really good, very stylish. Complement of an event. So we have an event. The complement, we write the complement as A prime. The complement of an event is all the things that don't happen in the original event. Should I say is complement of A is all outcomes that do not happen in A. So the complement of flipping a heads when you flip a coin is flipping a tails. The complement of rolling a 1 on a die is rolling every other number but 1. The complement of drawing a 2 out of the deck is the complement of drawing anything else but a 2. So the complement of event is everything that doesn't happen in the original event. Well, the nice thing about the complement is the probability of the event plus the probability of the complement. If the complement is everything that doesn't happen in the original event, what are the two probabilities going to have to add up to? 100%. Probability of A plus the probability of this complement has to give us 1. Probability of something happening plus the probability of everything else that didn't happen here has to be 1. And sometimes it's easier to calculate the probability of the complement than it is to calculate the probability of the original event. So we can say the probability of the complement, or the probability of the event, is 1 minus the probability of the original event. Or we could say the probability of A is 1 minus the probability of the complement. So sometimes it's easier to calculate the probability of the complement than it is to calculate the probability of the original event. And then we can use this idea to find the probability of the original event. So let's do an easy example that has to do with a complement, and then we'll be done. Any questions on what the complement is? All right. So let's say we roll 2 die. And we want the probability of a total less than or equal to 10. Now this is a pretty easy example because it wouldn't be really difficult to count up all the different numbers, different possibilities, the different ways that we can get less than or equal to 10. Well, let's think about, we talked about this, kind of like this problem earlier. If our event is less than or equal to 10, what is the complement of that event? Greater than 10. The complement is the probability of greater than 10. Well, didn't we calculate that already? What did we calculate the probability of rolling greater than 10 was? That's a probability of rolling 11 or a 12. The probability of greater than 10 is 1 in 12. So the probability of less than or equal to 10 is 1 minus 1/12, which gives me 11/12. And I'm just going to write over here, this is the probability of 11 or 12. So for this particular example, it wouldn't necessarily be that difficult to calculate the different numbers of ways we could get a total less than 10. But if we have a lot of things to count, it can be more difficult to count those things, and finding the probability of the complement is a little easier. All right, questions? Okay. Homework. There we go.